Good morning. Today's lecture is sampling theorem, and in this we have discussed so far what are the various sampling operations that we have considered while dealing with Z transforms or discrete time control systems. We have various types of sampling operations. Right, in that we have periodic sampling, the multiple rate sampling, multi-order sampling, and random sampling. In that we have different types of sampling operations, out of which we have considered that T, which is the sampling period, when we are going for sampling any continuous time signal. For example, you have any signal like this, it is T, x of t, it is a continuous time signal. When you are giving it to a sampler which is of time period, sampling period t, you are going to get an output which is x of kt, which is nothing but you can say kt, you can say it is x of kt, and 0, 1, 2, 3, 4 and so on. You can say that if you are sampling it like this, I am going to have a signal of this form. And we can understand here that t should be as small as possible. We can understand here that t should be as small as possible, so that we will not lose any information in between any two instants. So the curve which we are going to have in between 0 and 1, this curve, so much information should not be lost. So in order to safeguard that one, you are going to reduce the value of time t, or the time period between 0 and 1, or between 1 and 2. So in order to safeguard loss of information, we should not lose any information in between, so t must be as small as possible. So for that, when we go for frequency spectrum, we are going to see that omega s is the sampling frequency, which is nothing but 2 pi by sampling period t. Omega s is equal to 2 pi by t, which is where omega s is called the sampling frequency. Now we can understand here that when t is made as small as possible, omega s will be very big in value. Right. So we will have to consider in this x of t, which is our continuous time signal, we should first try and verify which is the highest frequency component that is existing in any continuous time signal. And omega s, for example, let me say the highest frequency component in this signal x of t, a continuous time signal x of t, is omega 1, then omega s is the frequency where we should be considering that omega s must be greater than 2 times that of the highest frequency component. So if this condition exists, then you can say that a signal can be sampled perfectly without losing any information, and you can also reconstruct back the original signal if this condition is holding good. That is, the sampling frequency must be greater than 2 times of the omega 1, which is the highest frequency component of x of t. So sampling theorem states that in any continuous time signal, if any continuous time signal x of t is sampled with a time period t, and if it has the highest frequency component omega 1, then the sampling frequency omega s, if it is greater than 2 times of omega 1, twice the highest frequency component, then the sampling can be done perfectly without any loss of information. And once we are trying to reconstruct back the original signal by using zero order hold or first order hold or any order which is applicable to that reconstruction process, then you can get back the continuous time signal as it is. Like we are having, this is x of t, then after applying zero order hold, the output of zero order hold also should be of this sort. This is h of t. This is the reconstructed continuous time signal from the x of kt, from the data sample data signal x of kt. When you are applying sampler to this, you are getting x of kt, which is sample data signal, and this, when you are applying to zero order hold, you are trying to get a reconstructed continuous time signal, and that signal also must be approximately, at least approximately nearer to this value without losing any information. So for that, the sampling theorem states that the sampling frequency must be greater than twice the highest frequency component of the continuous time signal that is applied to the sampler. So for this, we are trying to see two different methods of application of sampling theorem. We have two different methods. One is the graphical approach of understanding what is sampling theorem, and the other is the analytical approach. We will be discussing these two approaches of sampling theorem in this lecture, and this is nothing but Shannon's sampling theorem. In both these cases, we will try to see what is happening when omega s is greater than 2 times of the highest frequency component of the continuous time signal in both graphical approach and analytical approach. We will also see and understand if omega s, the sampling frequency, is less than 2 times of omega 1, what is happening? What are the various problems that we are going to occur, that we are going to face when you are going with omega s less than 2 times of omega 1. In brief, I will try to say that we are going to come across a new terminology called folding and aliasing. And there is also one more component, which is hidden oscillation. When hidden oscillation also occurs when omega s is equal to 2 times of the omega 1. So we are going to see all these factors when you for discussing sampling theorem. Now let us see the graphical approach. The graphical approach, you can say that for any function, continuous time signal x of t, let us consider x of t now in for all exists, x of t exists for all time t from minus infinity to plus infinity. Let us say we are considering any signal, a continuous time signal x of t that is existing for all time t. Previously we have considered in Z transformation, we have considered only one-sided Z transforms, and we did not consider two-sided Z transforms. Right, we have considered only one-sided Z transform, that is any function x of t is equal to 0 for all time t less than 0. This is what we have considered, but in this graphical approach or for sampling theorem, we are trying to apply sampling theorem to a function which exists for all time t greater than or equal to for all time t from minus infinity to infinity. So when you are trying to consider x of t, we will try to go and see what is the frequency spectrum of x of t. Frequency spectrum of x of t. Now let me say the frequency spectrum of x of t is given as x of j omega. Let me say that we can apply 0 and 1 and x of j omega, the modulus of x of j omega as the y-axis. For this, let me say we have omega 1 as the highest frequency component and the remaining any frequency components that are existing in x of t or x of j omega are less than omega 1. Therefore, we are only considering the highest frequency component. If we consider highest frequency component and if we consider omega s greater than 2 omega 1, the sampling theorem states that the signal can be satisfactorily be converted or sampled and can be reconstructed back from into a continuous time signal from a sample data signal. Therefore, we are trying to consider only the highest frequency component of x of j omega. So for this, let me say, if we are having any signal, the frequency spectrum of this form, let me say this is minus omega 1 and this is omega 1, and the magnitude of this can be considered to be unity. Let us say modulus of x of j omega is equal to 1, the magnitude is equal to 1. Now this is minus omega 1 and omega 1, that is in total we are getting, it is 2 omega 1. Now what is sampling theorem saying? Omega s must be greater than 2 omega 1. It means that this is 2 omega 1, therefore if I place omega s by 2 here and omega s by 2 here, you have this as omega s, therefore which is greater than 2 omega 1. As you can see that this is omega s which is greater than 2 omega 1. This bigger bracket is omega s and the smaller bracket is 2 omega 1. Therefore omega s is greater than 2 omega 1. In this condition we can state that we are having a higher, the sampling frequency which is greater than 2 times of the highest frequency component of x of j omega. Now in this condition, you can, if you are trying to represent x of j omega as, which is having a pole, x of j omega has a pole at s is equal to s1, and x star of j omega, these star transform which is represented here, this can be stated that it is, by definition we have sigma k is from minus infinity to infinity x of j omega plus or minus j omega ns, j omega s into n, where n is the number of samples, and therefore x star of j omega will be having poles at s is equal to s1, s is equal to plus or minus omega plus or minus j n omega s, and you have n number of poles. Therefore, with this into consideration, if I can extend this diagram and have poles at various values, you can say that this is omega s by 2, the similar distance, if I take it from here, if this is omega s and this is 3 omega s by 2, and here you have minus omega s by 2 minus omega s minus 3 omega s by 2, so on, minus 2 omega s, etc. You can also consider here as 2 omega s. Now if I consider this, I have one more pole, multiple poles that are represented here. You can draw it symmetrically, the distance between omega 1 and omega s by 2, and these two are the same, and here also you will have signals in this form. The frequency spectrum of this x star of j omega for various values, when you are having values of s poles at different positions which are repeated because of n s is equal to omega plus or minus omega s into n. Therefore you are having these values, and this is the place where if in this form modulus of x of j omega, x star of j omega, and this is the thing, then you are having at every pole you are having omega s is greater than omega s, the value omega s is greater than 2 omega 1, and therefore every pole, at every value you are having the frequency spectrum without any distortions. There is no distortion in this frequency spectrum which is drawn here. Now this is for omega s greater than 2 omega 1. Omega s greater than 2 omega 1. This is the condition. Now if we go for omega s less than omega s, let us consider omega s less than 2 omega 1. Omega s less than 2 omega 1. Let me see what is the diagram that we are going to get. For the same spectrum, modulus of x star of j omega 0 minus omega 1, and let me say we are having the graph in this form, and omega, this is nothing but 2 omega 1. And now what is the condition? Omega s is less than 2 omega 1. That is 2 omega 1 is this, and omega s must be less than that. Therefore minus omega s by 2 and plus omega s by 2 are here. Therefore, and with the same distance I can consider omega s here, 3 omega s by 2, 2 omega s minus omega s minus 3 omega s by 2 minus 2 omega s. Now at this here, at minus omega s, again you are having the function which is like this, and 2 omega s you are having, if this is not so far away placed, you can say we are having a signal like this and like this. That is minus 2 omega s, and here also there is some overlap that is occurring here, and at this point you are having some overlap here, minus omega. Therefore there is this overlap between these two functions. I think I have drawn this. Minus 3 omega s by 2 and minus 2 omega s. There is this graph here and this graph here. That is, you are having minus 2 omega s, minus 3 omega s by 2, minus omega s, minus omega s by s. Now you are having this as the folding region. Okay, so this is the region where you are losing information. That is, at any point in between these two, this is the folding region where you are having folding area, folding error. That is the error that is caused in this frequency spectrum when omega is less than 2 omega 1. It means that we are losing information, we are losing a set of information while sampling any continuous time signal. Therefore, we are losing the information in between. Here, we don't have that problem. When omega s is greater than 2 omega 1, we are not losing any sort of information. At every pole, you are trying to construct a sample data signal, and again you can also reconstruct back the continuous time signal. That is what sampling theorem is trying to tell us. When omega s is greater than 2 omega 1, you are having the frequency spectra which are placed or spaced equidistant from each other when omega s is greater than 2 omega 1. But here they are overlapping. This is the overlapping region. Overlapping two frequencies, any two frequency spectra are overlapping here. Here we are overlapping is possible, here it is possible, here it is possible. Therefore, overlapping, whenever overlapping occurs, the information that is there when you are sampling any continuous time signal will be lost when you are reconstructing back that original signal. Therefore, omega s less than 2 omega 1, you are having this. Now in this condition, we are having three different types of three different parameters that we will have to discuss. One is nothing but the folding or folding frequency or Nyquist frequency. Folding frequency or Nyquist frequency we can call at omega s by 2. Omega s by 2 folding frequency, which is nothing but omega s by 2, or Nyquist frequency, which is omega s by 2, which is nothing but, what is omega s for us? Omega 2 pi by t into 1 by 2, you have pi by t. Pi by t, where t is the sampling period, that is called the folding frequency or Nyquist frequency, and it is represented as omega n. So omega n is equal to pi by t. This is the phenomenon when folding occurs between any two frequency spectra. That is called folding frequency, over which omega s by 2 or minus 3 omega s by 2 or 3 omega s by 2 or plus or minus n into omega s by 2, you will have folding frequency or folding, and you will be losing information by sampling any continuous time signal or when you are reconstructing back the original signal. So that is called as folding. And the other parameter that we are going to discuss here is aliasing. Aliasing, what is meant by aliasing? Aliasing is alias. If my name is Ravi and Kumar, you can say Ravi alias Kumar. Therefore, aliasing is nothing but you are having two names for the same person. Similarly, you will be considering that you will have two spectra, two frequency spectral components at the same frequency. That is what we are trying to see here. For example, let me say we are having one frequency, let us say during this period, during this folding region or overlap region, omega 2. When this is happening here, what is happening when you draw a line here? You can say that you are having, this is omega s, this is omega s, and this is omega 2, and you are having, what is this value? The value here is this folding region. If you neglect, what is this? What is this point? Modulus of x of j omega 2. This value indicates x of j omega 2. At omega 2, what is the value of x star of j omega? You say it as x of j omega 2, right? And you have this value at this point. You will have one more signal, which is nothing but this should be the value. This should be the value x star of j omega 2, and you have one more signal like this, right, which is this condition. This is called x star of j omega s minus omega 2, x star of omega s minus omega 2 or j omega s minus j omega 2. So you have two frequency spectra that is existing here, right? So the condition here is you are having this value. This is one component of frequency spectra at omega 2, and this is the other component. That is, there are two frequency spectra that are existing in this when you are having folding frequency or when you are having omega s less than 2 omega 1. When you are sampling the theorem, when you are sampling any continuous time signal with a sampling frequency less than 2 omega 1, then you are having at that frequency, at any frequency omega 2 which is in between, you can see that for any signal in between this, that is where you are not having any overlap, then you can say that for any value here omega 3, you have only one value. At any point omega 4, you have only my modulus of x of j omega, this is x modulus of x of j omega 4, modulus of x of j omega 3, right? So these are the values that are existing here, right? There is only one value, but in between these two, in between this value or during this folding or overlap region, the overlap region, you are having two components, frequency components. One is the, if omega 2 is the frequency within the overlap region, then modulus of x of j omega 2 and modulus of x of j omega s minus omega 2. These two are the frequency spectral components that are existing. Therefore, there is naturally some distortion that is occurring. There are higher components that are higher frequency components that are introduced into the system because of folding or aliasing. That is called aliasing. Due to folding, there are two frequency spectral components that are existing, that are introduced. Therefore, there is distortion into the distortion that is introduced into this signal. Therefore, the original continuous time signal cannot be reconstructed back because there are higher frequency components that are existing into that are trying to be incorporated into the system. Therefore, errors are bound to occur, and such systems are occurring in various electromechanical systems when omega s is less than 2 omega 1. So, with this in mind, we can go for the, I will try to review what is the sampling theorem once again, so that we can go and understand a derivation part for the sampling theorem, so that we can analytically understand what is sampling theorem in this case. So once again I will try to write the heading as sampling theorem, and we are going with the analytical approach. In this analytical approach, let me say in the graphical approach what we have discussed: any continuous time signal x of t which is having frequency spectrum x of j omega, and it has got the highest frequency component omega 1, where now omega s, which is the sampling frequency, must be greater than 2 omega 1. When this condition exists, then the continuous time signal x of t or h of t, after applying x of kt to 0 order hold, there you will get h of t, the output of 0 order hold or any order hold will be h of t, which is a continuous time signal, and reconstructing back the continuous time signal from a sample data signal x of kt will be possible without losing any information when the condition is sampling frequency is greater than 2 omega 1. Therefore, with this in mind, we try to understand what is the analytical approach, and thus we can say this as Shannon's, the scientist Shannon has designed this sampling theorem. Therefore, you can say it is Shannon's sampling theorem, and this is the analytical approach. For this, we need to understand little bit of Fourier transforms. The Fourier transforms. What is any function x of t, any periodic function x of t which is existing from minus infinity to infinity, the Fourier transform of that function f of xt can be called as x of j omega, which is nothing but integral over minus infinity to infinity e power minus j omega t x of t dt. This is by definition, we can say that Fourier transform of any continuous time signal x of t which is existing from minus infinity to infinity, which is nothing but x of j omega, which is equal to integral minus infinity over infinity e power minus j omega t x of t dt. And the inverse Fourier transform of x of j omega is Fourier inverse of x of j omega. We can call it as, you are going to get back the continuous time signal x of t, which is given as by definition 1 by 2 pi e power j omega t x of j omega d omega, and this is infinity over infinity. Therefore, trying to use these two formulae, we are going to analyze what is the analytical approach for Shannon's sampling theorem. Now we know that x star of j omega is the signal, sample data signal that we are going to work on, and for this we know that without any lesser generality we can say that k is from minus infinity to infinity x of kt del of t minus x of kt into del of t minus kt. This we have already discussed or found out, where for applying Laplace transforms in our previous class we have obtained x star, the star Laplace transform x star of s is equal to sigma k is from 0 to infinity x of kt del of t minus kt, where del of t minus kt is the train of impulses, where x of kt gives you the magnitude at that particular instant. So this can be used here without any hassle. So x star of j omega, which is sigma k is equal to minus infinity. Now when you try and apply that here, x of t x star of j omega is equal to integral minus infinity to infinity e power minus j omega t, and